All right, so let us start. Again, slides are online. You can search Eamonn's name and go to UCR matrix profile page 2. So let's reconvene. In the first half, what you have seen is how matrix profile is applicable in various domains and give you diverse set of knowledge that you can gain without understanding the data or looking at the data in depth. So this half, we will describe algorithms. So it's totally different. As Eamonn explained, there is an abstraction. So this half, we'll talk about algorithms, numbers, pseudocodes, and stuff like that. So probably some of you will be more interested in this. We embed MATLAB scripts, very small, tiny scripts, to explain algorithms that can reproduce the charts and numbers that I used in this part of the tutorial. And slides are, like before, text heavy, so you don't have to read them. Just follow the pointer and follow the figures. That is more important. So let's begin. So who am I? So who am I? I'm that guy, seemingly unrecognizable now. So I will start with background, assuming that you have never worked on time series before, and give quick description of things that we will assume known in the rest of the tutorial. So I'll start with distance profile, which Eamonn hasn't mentioned, but is an integral part of matrix profile. So we need to understand distance profile to understand matrix profile. I'll tell you about the algorithms that can calculate this distance profile in an iterative manner. And then I'll show some of the extensions of distance profile. And finally, I'll introduce the algorithms that calculate matrix profile. So that connects the first part and this part of this tutorial. And then I'll tell you some open problems that I would love to solve myself. Some of them I cannot solve. Some of them I don't have time to solve, or something like that. So let's start. So we define what is time series, right? So there are many definitions, and the question answer section also revealed that people are thinking about time series in different ways. So for this tutorial, we define time series as a collection of observations made sequentially in time. So we have a sequence of real numbers, like this blue vector here. And if we plot it, what do we mean by plot? We just have those sequence of numbers as a point and connect them by lines. Then we see beautiful pictures like this, and you have seen enough of those in the first one. Sorry. So this blue vector is this time series here, shown in blue, 2 heartbeats. In the x-axis, we have only the index of the observation. And if a time series is sampled at equal intervals or equally equispaced manner, then basically you don't need the exact timestamps. All you need the order of the individual observations. And that's what we have here. In the y-axis, you have some values which possibly have units. And in this case, it is some electrical potential. And if you think about like the sparse time series, missing value time series, or different scaling, factoring, those things, for now, let's exclude them from consideration and just focus on real valued vectors. And do they have to, the time series, do they have to come in order of time? No, it can come in any order. So it can be, say, a shape unfolded about the centroid and created a sequence. Or it could be text. You just take the envelope from left to right in that order and make a time series. You can convert ASCII text to time series based on the left to right ordering of the text. So anywhere there is an ordering, you can convert it to a time series. Then question comes is that given 2 time series, how we calculate the similarity between 2 time series? And there are many ways, and also we will be using similarity measure and distance measure kind of in a synonymous way because they can be converted from one another. And largely, if you categorize the similarity measures, there are 2 types, right? First, lockstep measures where you lock the observations based on their index. So ith observation is compared with ith observation. So you lock that. And you don't look around. So every observation is only compared or matched or aligned only against the corresponding observation in the other time series. And you know some of them. We will go in detail, obviously, mathematical definitions. So lockstep measures, the examples are Euclidean distance, correlation coefficient, cosine similarity. And as opposed to that, if you allow the flexibility that, OK, I'm going to match ith sample with some of the samples around ith sample in the other time series, then basically you come up with an elastic measure. And there are examples like dynamic time warping, added distance, longest common subsequences, and so on. So again, in this tutorial, we are going to assume we are working on lockstep measures, not elastic measures. All right, so let's define first, since we have Euclidean distance here, let's define Euclidean distance first. So we have x, a vector with n observations, say, y, another vector, n observations, and the blue and the red ones are there. So the z-normalized Euclidean distance, so Eamonn mentioned about z-normalization. We'll talk about that a little bit also here. So the z-normalized Euclidean distance is defined in this way, that you take the x observations, subtract the mean of x, and divide by the sigma, or standard deviation of x. So the standard deviation here is the sample standard deviation, as opposed to the populational standard deviation. And a MATLAB script is very simple. So you can have a function called z-norm, which takes in x and produce a normalized value and output it in y. And you take the vector, subtract element-wise the mean, and divide element-wise the standard deviation. And that small 1 corresponds to the fact that it is a sample standard deviation, not populationalized standard deviation. Very simple. You normalize the two sequences. Then you calculate the Euclidean distance. Very simple. You subtract. So we use hat to represent the normalized values. So just a disclaimer here, in this part, you will see equations. So if you felt bad that in the first part there was no equation, then you'll have it here. And if you feel the other way, then bear with me. I will have some visuals, some fun stuff. So OK, so you subtract the hats, or the normalized values, square them, sum them, and square root them. And that's exactly this Euclidean distance function is in MATLAB, right? So this dot square 2 means element-wise squaring. And what it means visually, it means that you bring down whatever. So purposefully, I excluded the y-axis, right? So you z-normalize them, and they go down between, say, standard normal distribution, minus infinity to infinity, but mostly around 0. And once you bring down in the normalized space, you can take this area between the two time series as the distance. And that's exactly what Euclidean distance refers to. So if two time series are very different, then there is a higher area, larger area between them. If they are very similar, then there is a very smaller area between them. So let's define correlation coefficient. And this is important because we will merge them, the lockstep measures, and see what's more important, right? So given two time series x and y, this is how correlation coefficient is defined. Like if you go to a textbook, that's how you will see. And in this talk, we will be using this formulation, a relatively rarely used, but very good for us. Why? Because it has 5 elements. So if you think about it, I'm spelling it out. So this is the dot product. Here in this case, the vectors are size of m. You use the dot product between the two time series x and y. Subtract the m, which m times mean of x and mean of y, and divide the whole thing by m times standard deviation of x and standard deviation y. And this standard deviation can be calculated in this way, and the mean can be calculated in this way. And in turn, if you think about this whole thing, the bottom line is you can calculate correlation coefficient only using these 5 sufficient statistics that are linearly calculatable. So you can scan the time series from left to right and calculate the dot product, sum of x, sum of y, sum of x squared, sum of y squared. And then you can calculate the correlation coefficient. So that is the most useful part. So if we have correlation coefficient like this, then question is, what is the relationship between Euclidean distance and correlation? And this is the relationship. So you see correlation in the y-axis between -1 and 1, and the normalized Euclidean distance between 0 and some positive number, which depends on the length of the time series. In this case, it is 100, and for 100, the maximum Euclidean distance in the normalized space you can have is 20, and that's fixed. It cannot go more. And this relationship is expressed in this formula, which is the Euclidean distance between two normalized sequences is equal to square root of 2m1 minus correlation of those two sequences. Known fact. Correlation coefficient is not a metric, but Euclidean distance is. So correlation coefficient doesn't obey the triangular inequality, while Euclidean distance does. And the fact that they are monotonic, maximizing correlation is equivalent to minimizing Euclidean distance and vice versa. So now if we plug in the correlation formula here, we get this. And this is the only equation that I would like you to focus on and remember over the course of the presentation. You don't need anything else. So the distance between the two normalized sequences, I just plugged in the correlation formula here. And this is our working formula. And you can see that if you want Euclidean distance, Z-normalized Euclidean distance, you work with the whole thing. If you want correlation, you work with this whole, only this part. If you want just cosine similarity, maybe you just work with the dot product. So they are all kind of in this thing. And we claim, or in this tutorial at least I claim, that if you have a matrix profile algorithm for Z-normalized Euclidean distance, then you have a matrix profile algorithm for correlation coefficient, you have a matrix profile algorithm for cosine similarity, and other lockstep measures. So that is the claim and purpose of the last 3 slides. All right, so you can now argue that why Z-normalization? That is a key question, people may say that, right? There was a question before in the first part that why Z-normalization, right? So there are domains where you may want absolute value, because 105-degree fever is itself enough to say that it's serious, right? You don't need, is it rising or going down or not? You don't need it. Absolute value, 105-degree fever, body temperature is enough to say that you have to do some intervention, right? So there are some cases like this, but we are not interested in those. We are interested where the relative changes are important. And in this case, say we have 2 heart failure EKGs or ECGs from 2 different persons. Both had congestive heart failure. And the red one and the blue one, we overlay on top of each other. And then what we do is we extract each individual bits, and without normalizing, we show them here. So the red one and the blue one, you can see that their means are relatively same, while they have, this one has a little bit larger standard deviation, and this one has little less. So from this, you can claim that, OK, if I want to make a classification task, I don't need to normalize them, because their means and variances are very same, very similar, so I don't need them. I can just use them as they are and do a, say a clustering task. So let's see what happens. If you do that, then basically in the unnormalized case, you will find that some of the reds and some of the blues, like these two, are more similar to the reds than the other blues. And if you normalize them, basically you wash out that difference, you make everything with the same mean and same standard deviation, and then the clustering results look perfect. So what is the bottom line? The bottom line is that even if you see them, that OK, they are very similar in mean and standard deviation, and feel like, OK, I don't want to normalize, that's an extra step, and that costs me expensive computational time, I will not do that, I'll just do work on the raw data. Then basically you can have situations like this. So the overall suggestion is that normalize your data, then most of the algorithms and matrix profile algorithms and its use cases will be applicable to yours. So that's the background, just that you need to know to understand the algorithms. And I'm going to talk about distance profile now. So distance profile, you have, this is the definition. So you have a big time series, which has a length of small n. This is true for the next 1 hour. So you have a big time series of length n, and you have a query, which has a length m, small m. And your goal is to do similarity search, meaning that you extract the sliding window. So you take a window, you slide it across the time series, extract each window, calculate the Euclidean distance between the query and that window, and store it in this vector. Obviously, if you have n-sized query and n-sized time series and m-sized query, then you will have n minus m plus 1, that many different distances. And if you store them in a vector, then that is the distance profile. That's what we say. So basically, the distance between the query and all possible subsequences of the time series. So that's the definition of distance profile. Then the question is, how can we calculate that, right? And very simple brute force algorithm here. So scan the time series with a sliding window. Here is a MATLAB script. I'm going to explain that. So you take a vector of size n. It can be n minus m plus 1 size, whatever it is. You put zeros there just to initialize. And then you normalize the query. I showed that function in a few slides back. And then you scan, which is your sliding window operation. You scan from 1 to n minus m plus 1. So you the I is the starting position of your window. And you extract the subsequence I to I plus m minus 1, which is from the time series t. Capital T is the time series. So what you do is you normalize the time series on the fly, because you don't know which time series you are going to do it. If you do it ahead of time, then you'll have to store it. And that will cost you almost nm space. You don't want that. So you normalize it on the fly, subtract the query, square the elements, sum them, square root them, and you get the distance. Very simple MATLAB script. How long does it take? It takes this much time. So in the x-axis, so we'll reuse this plot. So it'll be good to explain the axis. So x-axis is n. So this is log scale. Y-axis is seconds to process that, to calculate the distance profile. So both are log scale. So this is almost an hour. So for 100 million long time series, if you want to search a 100-point long pattern, then you will need about an hour on a standard commodity box. Obviously, we want to do better. How? So that's the question we will answer repeatedly. But at this case, you can see that this algorithm takes order nm time, meaning that for each window, you'll have to pass the query at least once, scan the query at least once. That's why it is order nm. And the average and worst case is identical. They're identical. So how can we improve that? That is the first question. So we have already seen that, right? So we can actually avoid calculating the normalization within the loop. Instead, we can use our working formula. And we can, if we know the means and standard deviations and the dot products, then we can calculate the z-normalized Euclidean distance on the fly without normalizing the sequence. And we are going to use this observation, which is a very standard result in the everyone knows in statistics, elementary statistics, that z-normalized sequences has 0 mean and 1 standard deviation. So if you assume that your query will always be y in this formula, then you can refactor this or imply from that you need only the dot product and the standard deviation of the sliding window. So only the 2 terms you need, the dot product and the standard deviation of the sliding window. So we use that factor, that observation. And then question is that, okay, let's assume that we can calculate dot product with 1 scan. How do we know this standard deviation? Can we pre-calculate that in linear time? And answer is yes, right? So you can pre-calculate standard deviations for all the sliding windows in linear time. And that's how you do. You just take the cumulative sum of the vector, take the cumulative sum of the square of the vector, and then you take subtraction of m points apart. So you subtract m from I, 1, then m plus 1 from, sorry, the other way. You subtract 1 from m, then 2 from m plus 1, 3 from m plus 2, and so on. And that way you get the sum of each window. And then finally, you use this formula to calculate the standard deviation of a certain window. And this is a very straightforward operation. And you may say that, OK, what is unique, novel about this, right? So interesting thing is, and it's not that we have published it in 2012. And it's not that we are showing that, OK, this is a novel algorithm, right? The thing is that this has a great use in temporal data mining. That's what we showed in this paper. So, and that the effect is that in 2016, MATLAB introduced a function moving a standard deviation, which does exactly that thing. And it's not that we invented that algorithm, and that's why MATLAB did that. It's because that this algorithm is useful in many ways. So as you understand that if you can calculate moving standard deviation, you can calculate moving median, moving mean, and so on. All right. So how do you use that, right? So if you can scan the time series once for the sum, and then you can calculate in another scan, you can calculate all the standard deviations. How can you use that? You can use it in this way. So anytime I introduce a change in the code, I will highlight that. So the other lines are same as before. So I'll not explain those. I'll only talk about the highlighted section. So this section is basically talking about the just-in-time normalization, meaning that instead of calling that z-norm function, you will use our working formula, where you use the square root of 2m 1 minus sum of this. Basically, this is the dot product, and this is the division by standard deviation. And that standard deviation is calculated using this moving standard deviation formula. So only these lines of code will give you a just-in-time normalization, meaning that whenever you are calculating the distance, you don't have to normalize explicitly, you just use this formula. And that gives you this much speed up. From that, you go down to this. And it's more than 2 times, because you not only removed one scan of the data in your loop, you also removed a function call, and that's why you get a little bit more speed up. And this is, some of you may be thinking that, OK, this guy is showing speed up on MATLAB code, right? I mean, come on, we do cloud, we do GPU, a lot of things. But these speed ups are reproducible in any platform, in any language. Say you say Python or something like that. These are core in the algorithm. OK, so again, the worst case complexity is still nm, because we scan the entire time series, and for each subsequence, we calculate the distance explicitly. We need to do the dot product. Can we improve that? And here comes the other algorithm, which is called Mueen's algorithm for similarity search. That's kind of evil in a way that I'm discrediting kind of my colleague's work, but that's not the purpose. It has to be named something, and mass is a very simple, cool word, so that's what we are using. But I give full credit to my co-builders, Jan and Michael, sitting there. All right, so the question is, and you will see that as we are developing this algorithm, there is not like a great ingenuity, like say doing super tricky things or something. But the fact that we are stitching together a lot of small known techniques to solve this time series similarity search problem is really effective. So what we do in mass, we use convolution based method, or convolution, to calculate sliding dot products in order n log n time. And we also use our just-in-time normalization technique. And if you don't know what is convolution, convolution is, if you define in a simpler way, if x and y are vectors of polynomial coefficients. So if you think that x is the numbers in x are coefficients of a polynomial, and numbers in y are also coefficients of polynomial, then basically convolving them, meaning that you are multiplying those two polynomials. I'll show you an example shortly. And we will use convolution to calculate the dot product. So what does that mean? So let's say we have a toy example. We have the time series, which is only 4 points long. And we have the query, which is only 2 points long. And if we use that as an input, then to calculate the sliding dot products, that's what we need. We want to calculate the first dot product, which is y1, x1, y2, x2. That's exactly here. Then y1, x2, y2, x3. That's exactly here. And y1, x3, y2, x4. That's exactly here. So we want to input this, produce this, and the convolution operation is this. This is the simple polynomial multiplication. That's how you do it, right? So you multiply the first n degree coefficients, and then n minus 1 degree coefficients, and so on. And you can recognize the symmetric pattern here, right? So our goal is to move or pass the input vectors through this convolution operation to produce this. Now, if you directly do that, then what will happen? X1 will be multiplied with y1 in this operation. So this green line means that you are multiplying this guy with that guy. These green lines mean you are multiplying this guy with that guy plus this guy with that guy. So that is the operation we are doing. So if you just take the straight vectors, then it doesn't work. The way you do it is basically you keep the time series as it is, but you reverse the query from y1, y2, you reverse it, and then append some zeros until you make it equal to the size of the original time series. So if you do that, then this operation, this operation will produce this vector where the middle three numbers, are exactly what you want. You can see it. For example, if you do this, then x1 multiplied with y1 and x2 multiplied with y2, and that's exactly what you have in here. So if you do this, then you will see that this x1 is multiplied with this 0 and canceled out. So this is the key operation. So basically what you're seeing that how you can use convolution, the very standard technique in signal processing toolbox or in anywhere you can see a very standard convolution technique. You just do that, and you have all the sliding dot products in order n log n time. And very good thing is that there is no m here. And that's what Eamonn meant by the fact that there is no curse of dimensionality. So whatever m you choose, whatever the query length is, the dot product, getting the dot product takes equal amount of time. So how we use it? We basically, this is our algorithm, and this was the previous algorithm, just for a reference, and you replaced this loop with this thing. So you take the query, and you reverse it. N to 1 minus 1 is the increment. So you reverse it. And then you append from m to n, from the query length m to all the way till the size of the big time series, you pad with zeros. And then you convolve them. And then basically that gives you the dot products, all the dot products. And then basically this is the vectorized operation to calculate all the correlation or Euclidean distances in one line. And then finally you do the square root. You can merge them. I just had them separate. So n log n algorithm, free of curse of dimensionality, no loop, only known built-in MATLAB functions are used. How good this code is, right? So that's the question, next question. So this is the output. So the just-in-time normalization is the blue one, and you reduce using this version, let's call it mass 1.0, because we'll iteratively improve it. I don't know what happened to that point. Maybe I was playing a game or something. And suggestion, don't play games because it'll ruin your result. OK, all right, so definitely that's an outlier, but the trend is clear. All right, so how can we improve it further? So question is, can we improve mass 1.0? So we have seen the convolution. And the observation that is that convolving doubles the size of the input vectors. So if I go back, previous slide, so we convolved, and we produced, from the size of 4, we produced 7. So we doubled. 2n minus 1 is the output of convolution of n-sized vectors. Forward. So So convolution doubles the size of the input vectors, and mass only uses half of the output. It doesn't use all the 7 output numbers in the vector. It uses only the 3. How can we calculate only the 3 and don't calculate the other half? That's the question. And to do that, we are looking into the convolution operation. So what happens when you convolve? In picture, we have seen that this is what happens. But what happens in code or in numbers, right? So the convolution operation this is a known theory, right? Most of us know that convolution in time domain is multiplication in frequency domain. Solid theorem, right? So that's kind of the basis of many modern marvels we are seeing. So the convolution is essentially this thing. So what you do is you take the x, you double and pad it with zeros. You take the y, you double and pad it with zeros. Do a multiplication of the frequency terms, and take an inverse Fourier transform to go back to the original domain. And that's exactly the definition of convolution in mathematical terms. So FFT, if you need to recall, it is fast Fourier transform and produces the complex numbers, which are the frequency terms in the frequency transform. So if I look at pictorially, it is like this, that if you have the input vector x1, x2, x3, x4, then you double it and pad it with 0. We had our query vector, which is y2, y1, 0, 0. We double it and pad with 0. Then we take the Fourier transform, and that produces a vector like this, which are vector of complex numbers. But there are some properties of that, right? So first property is that if you have a real valued vector, then the complex numbers in the Fourier transform should be symmetric, meaning that the second one will reappear as a conjugate in the last one. The third one will reappear as a conjugate in the second last one. The fourth one will reappear as a conjugate in this third last one, and so on. So that's what is happening here. The same thing happens here. So these are symmetric. And then you multiply them. So x1 gets multiplied with y1 here. Then say, for example, x3 gets multiplied with y3's conjugate here. So that's what we have here, and so on. And then once you inverse Fourier transform this vector, you get the desired output. That's what happens in the background when you call this convolution function. And the solution for the interest of computing only the necessary part is that you don't double. Don't double. So instead of doubling, you just take the Fourier transform of x, take the Fourier transform of y, multiply that, and take the inverse Fourier transform, and we call it half convolution. And if you do that half convolution, basically this whole thing, I just showed it, this thing. So if I go back, this picture here is identical to this picture here. And this, if you don't double and pad, it becomes like this. And again, here you have the conjugate and the vectors, Fourier transforms, multiply, inverse Fourier transform, and you get this one. And this is how you can actually say that, OK, I'm going to do this operation manually. I will not use the convolution function. I'll do it manually in a half convolution way, and then I'll get the desired output. And pictorially, it looks like this. Instead of calculating these unnecessary 3 numbers, it will be creating only the necessary 3 numbers, plus 1 additional number. So what does it add? Like, we are saying that we'll not do something. But does it add some constraint? Yes, answer is yes. So you add the constraint that n must be larger than m over 2. Oh, sorry, I think it's the opposite. M should be larger than n over 2. I'm sorry. No, wait. Yes, n should be larger than m over 2. And no, I'm confusing. But let me restate. N over 2 should be larger than m. Okay, so that's the idea. N over 2 should be larger than m. So basically, what it means that the query must be less than half of the original signal. If it is more than half of the signal, then you cannot do half convolution. That is the statement. Okay, so change the code. Let's change the code. So we had this thing, and we change this line, instead of convolving the query and the time series, we will use this manual convolution, kind of half convolution. So we'll not use the convolution function as it is. We will use Fourier transform and then inverse Fourier transform to calculate that. How does it do? So the complexity remains the same. Instead of convolution, we are using Fourier transform, fast Fourier transform, and that gives us mass 2.0, which is faster, because you don't do half of the calculations. Can we improve this? Right? So can we improve mass 2.0? And again, we are using another technique, which is called the overlap add, overlap save. So basically, you divide the big time series, the n-sized time series, into pieces of powers of 2, because we all know that Fourier transform works better on powers of 2, right? If your time series is, say, 2 to the power 10, 2 to the power 20, or 2 to the power 30, you can have a better performance compared to other odd numbers or other length of time series. So then question is, what should be the piece size of the pieces, right? So let's say we divide in pieces of size k, right? So basically, this will be the case. So you have first piece of size k, and then second piece of size k, third piece of size k, and they have to overlap at least m-1 sample. Actually, exactly m-1 sample, because if you overlap less than m-1 sample, then you will lose some of the distances. If you overlap more than m-1 samples, you will be essentially calculating some redundant distances. So you need to overlap them exactly m-1 samples. And obviously, the last piece can be smaller than k. It has to be, smaller than or equal to k, and it can be any odd number, but we'll assume that we'll process that with the overhead of Fourier transform. Then question should be, what is the ideal size of k, right? Should we chunk it like, say, every 5 points, or 10 points, or 200 points? So we vary the k here in powers of 2 from 1024 to a big number, 400k. And then we measure the time, and we see that it decreases, and then increases. And what is this magic number, like this 2 to the power 16, right? Why for sizes of 2 to the power 16, we have the least computational time? And the reason is very simple. Basically, it matches with the word boundary of the machine or of the hardware, and that's why all the cache misses go out and all those good things happen, and you have a minimum value here. Obviously, it's hardware dependent. If you run it on a smaller, say, in your iWatch, it will be different and so on. Wherever the system has a different configuration, you may have a different k as the minimum. So this is a system-dependent thing. But let's say we calibrate our system, our code, and find the best k. Then how much speed up does that get? This gives us the mass 3.0, which gives us a little bit in the log scale. That's reasonably good. So at this point, we started from here and bring it down to here, which is for 100 million, it's 11 seconds in MATLAB. And still, if you want interactive speed, yes, 11 seconds is OK for interactive speed. But I think you want to bring it down, right? So at this point, I will stop and say that this is the software techniques up to this point. And I will have to invent something new, right? So I can name, if you ask me, like, how can we improve it? There are ways, like, say, you can say, OK, design a new application-specific processor. So you design a processor that does very good FFT, very fast FFT. You can beat the performance here. You can say, no, I'm not going to do FFT, but design an application processor, which costs more. So I will be keeping the general processor and optimize the RAM access. You do better. And then you can say, no, I'm not going to do that either. I'm going to keep the commodity machine and add a GPU, and I'll do better. You can say, no, I'm not going to add a GPU. I'm going to add an FPGA card, and I'm going to do better. You can use approximation also. You can say that, no, I'm going to calculate FFT in an approximate way to gain speed, and then I will use mass to calculate the similarity metric, distance profile, and I'll do that way. So whatever way you choose, like, and as you see, these people have worked on those things. We haven't merged them, but the thing is that the mass algorithm can easily be benefited from all this work that optimizes Fourier transform, which is a very important research area for many people. So once we integrate those, my hope is that we can actually bring it to sub-second level. And for, say, 100 million long time series, we can search it very quickly. All right, so some notes. So the code here, which is the code that we just developed, has some challenges, right? Because if you do inverse Fourier transform of the multiplication of Fourier transforms, there can be numerical errors. And we basically, if you have n equals, say, 1 billion, you will see the coefficients are a little bit off from what they should be because of the summing of a lot of numbers, right? So, and if they are positive numbers, then you will accumulate errors. Large numbers will eat up the smaller numbers, right? Because they are real values, and computer has a finite precision. So that can happen, and the mass 3.0 by chunking actually takes care of that. The second problem is the standard deviation. It can be 0, right? And then you'll have a divide by 0 error. And when will it happen? It will happen when the signals, the query, the subsequence from the long time series is a constant segment. And Eamonn has showed one such time series, right? So a constant segment has a standard deviation of 0, and you cannot process that here. So if you input a time series with a constant segment, then it will produce divide by 0 error. So you'll need a explicit manual check here that, okay, standard deviation is not 0 or not within an epsilon to make sure that you don't get into that error. And the final one is square rooting. When you square root, if it is a negative number, then you can have a imaginary number in the output, which is theoretically not possible because Euclidean distance is always positive. It cannot be imaginary. So when does that happen? It happens when you have two sequences. Say you have the query, which is from the time series itself, meaning that it matches with your time series exactly, and the distance is 0, then maybe your distance value here will be something very small like this, but with the negative sign. And then it'll get an imaginary number and produce an kind of odd distance vector, distance profile. So a few things you can do. You can take the absolute values only and solve it. Or you can check in here before taking the square root if there are any negative numbers. That has to be very small like this, and then you can convert it to 0 and then take the square root. So these manual checks, by manual I mean that explicit checks, should be done in the code so we can actually process signals with constant segments, exact matches, or for longer signals that can have numerical errors. All right, so at this point, I will say this, that so far we have covered this. So distance profile, brute force, just-in-time normalization, and mass. And I will show some extensions of mass, and I'll call it rest zone, because 1 hour 15 minutes is too long, right? So to pay attention, keep your concentration on. So it's rest zone, so you can stretch and like be a little relaxed. Because these extensions are not directly related to matrix profiles. So I'll show you some extensions of mass, but you can be relaxed, okay? All right, so what is the first extension? Question is, can we speed by trading accuracy, right? So we don't want accuracy, we want speed. So yes, you can. We can trade speed with accuracy in mass. So basically, this is the piecewise aggregate approximation. So you divide the time series in windows, non-overlapping windows, take the mean of the sequence here, and then you convert the red time series to this, blue time series to this, which is much smaller in dimensionality. And then you take the distance in this dimensionality, which is much smaller than this. And then you move from here to there by multiplying a square root of w, which is the length of this thing. And then basically, you don't get the original distance, but you get a lower bound. Meaning that if you reduce your dimensionality from here to here, you gain speed because you are summing only m over w, that many numbers, and you multiply it by square root of w, then you don't get the original distance, you get a lower bound. But if you have that, how does it help? So you can say that instead of doing the mass on T and Q, what I'm going to do is I'm going to piecewise aggregate approximation of t with a window length w. I'm going to PA q with a window length w, and I'm going to use the input m over w as the window length. And after the mass produces the distance profile, I'm going to use this square root w as a factor. And basically, it means that if you use, say, w equals 2, then your red and blue matrix profile, sorry, distance profiles are very identical. So red is the approximate one. If you use w equals 4, then red is a little bit off from the blue. If you use w equals 8, then red is a little bit more off. But as you understand, w equals 2 means 2 times the speed up, w equals 4 means 4 times the speed up, and so on. So you are trading accuracy off by gaining speed. Very simple. So speed up. You can still relax. No worries. And then here, the weighted query. There are some equations here. Don't look at those if you don't like them. So the picture tells the story here. So you have a Euclidean distance between red and blue, which is the total area. And like the annotation vector that Eamonn mentioned, which is on matrix profile, but in this case, we are working on Euclidean space. And we say that we have a weight vector. And we define the z-normalized weighted Euclidean distance. Basically, we say that by taking the subtraction, squaring it, after that, we will multiply it by a weight. So each number here has a different weight. And then we take the Euclidean distance. So if we do that, then we should put some constraint on W. So number of elements in W should be exactly m. And then the W, each element here should be positive, and their sum should be 1. We can add this constraint. And then basically, if we have a W like this, which means that everywhere it is 0 and here, then basically it means that you are saying that I don't care about the left side and the right side. I only care about the middle part, and give me the area between the two time series in the middle part. That's what you are exactly asking for. And this kind of weighted time series distance, similarity search, it creates more problem for mass. And you don't have to look into the equations if you don't like. The bottom line is that previously we saw in our working formula that we need 1 dot product. But if you have this weight term, then you will need 3 dot products. And that will cost you 3 times more time in calculating the mass for weighted queries. So that's the bottom line. You can check if the equations are correct. If not, please let me know. Example. So how does this weighted queries help? So you have this time series. Say it's a hot water usage in a house. So you measure how much hot water the household is consuming in minutes. And then you have a typical cycle, washer cycle. So how does your washer work? You have some washing cycles, and then a gap, and then you have the rinse cycle. And you say that, OK, I have this query. Can I search for other occurrences? Yes, in this data set, you have many such washing cycles, washer cycles, then rinse cycles. Now you say that, no, I want to see that what happens in between. I don't care much about those. I want to see if there is any any different pattern that we can see here. And what you do is you put relatively low weight here and, sorry, the other way. You put relatively high weight here, and low weight here, and want to match this 0 segment to anything that you can see in this whole time series. And you output this. So the weighted Euclidean distance profile will output this. And basically, you can see that this thing now matches with this red guy, which has some additional cycles. Sometimes you have more dirty codes. You say add some cycles. Sometimes you say extended cycles. You turn the knob and make it run for longer. So those things are appearing here. So you can actually search for alternate notions of your query, right? So not the exact one. And those will also be answered by this weighted query formulation. Final thing. So queries with gaps. Sometimes you say, I mean, we already have seen an example where queries with gaps. So you want a query where the left and right matches, but not the middle one. But you can actually say a little bit more complex thing. You can say that I want the first third to slope down, then 1/3 of gap. I don't care what's there. And the other third, you slope up. And you don't mention what should be the slope. You just say it's the slope. then basically both of these can be a match, right? So you don't care about the middle, and the first and last segment, they can be anything. Note that they can be anything, meaning that they scale individually, independently. So they can be shifting and scaling in their own way. So if you have such a case, then basically what you'll do is you will take the query, and if the first point and first point here, they are L points apart, then you'll do this algorithm. So basically you will measure the distance between beginning of the two patterns. So basically what you'll do is you'll use query subsequence 1, which is this one, create a distance profile using mass. You take the query subsequence 2, create a distance profile using mass independently, and then you will shift distance profile 1 with the distance profile 2 by L element, and then you sum the distance profiles. And if you sum the distance profiles, then the final distance profile will give you the nearest neighbors of this query in the way that you want, in the way that the individual subsequences scale and shift independently, and may produce results like this, that say if it is a random walk and you create the distance profile, you add some sliding, some lags there, you add these two distance profiles, sorry for the faded pictures, and then once you sum this, then the minimum value here will give you the nearest neighbor, and the match will be something like this, that the first slope kind of matches the query, but the second slope going up will be a scaled and shifted version. So if you want those kind of independent scaling and shifting in your query, that is the query with gaps, and you will follow this algorithm that I just have here. So enough stretching. So we will be now starting the matrix profile, and as I said, the weighted query, approximation, the gaps, forget about those. Let's just refresh our mind that we have mass, which is a distance profile algorithm. We can just create the distance profile in order n log n time. How can we use it? So what we are going to do is we are going to get the matrix profile from distance profile. So recall the matrix profile definition. So until now, we haven't talked about that, but now we are going to see the real thing. So previously, we saw that for distance profile, you have a query here, and you slide the window here and calculate the distance. Now you don't have a query. You take the query from the subsequence itself. So you have, say in this case, the first subsequence, which is this window, and you slide this window here and calculate the distance from that, and you fill in the vector. Obviously, the first distance will be 0, right? And that gives you the D1 instead of just D. D1 is the first distance profile of your time series. And obviously, you can slide this window a little bit and get D2. You can slide the window next the sliding window and get D3, and so on. And at most, you can get Dn minus m plus 1, that many distance profiles. Now imagine that take those D1, D2 up to Dn minus m plus 1, and you stack them. And that's what your matrix, right? That's why we call it matrix profile. So you have this distance matrix where each ij value says this is this distance between ith window and the jth window of the time series. And the properties of distance matrix is that it is symmetric because it is the same time series. We are doing a kind of a self-join thing. So ith time series, ij and ji are kind of the identical distance. And what we essentially do to create the matrix profile, we take column-wise minimum operation. So we calculate the minimum of the column, put it here. So P1 is the minimum of all these values, and which is effectively, since it's symmetric, the first column and first row are the same, and first row is the D1, so you take minimum of D1 and get into P1, and so on. So this is your matrix profile, P. Question is, how do we calculate it, right? So do we need to enumerate or kind of absolutely realize or materialize this whole matrix? Answer is no, right? Because you have mass. So basically what you'll do is you initialize your matrix profile with some numbers, say infinity, and then with some big numbers, and then you will calculate all these distance profile using mass and take element-wise mean with this thing, right? So you calculate this distance profile, take a minimum with this vector, and store it here. Then calculate this distance profile, take a minimum with this vector, and store it there, right? So very simple. Complexity is order n for space, and order n square log n for the algorithm, the time, because this loop runs n times, and this algorithm here takes n log n time, right? So you have an n square log n algorithm to calculate MP. The key part here is that note, the space complexity is only order n. That's the key part, because previously we really didn't know how to calculate this profile without spending more than linear space. Because we will see the comparison, the existing techniques, they all store the z-normalized sequences explicitly in the memory, and that gives them the chance of reusing computation. And that's what gives them speed up. But once you store them, you need order nm space, and that's quite huge. For example, in case of 1 million long time series and say 1,000 long query, you will need 1 billion numbers to store. And that's way too redundant and space consuming. Question is, can we make it better, right? So, but before that, let me also say that, okay, since we need the matrix profile index, does it add any overhead, or is it costly? Actually, no, because you keep a matrix profile index as your iterative variable, and basically you initialize with -1, and whenever you calculate the minimum, you update the matrix profile index as well. This is too much MATLAB dependent, but you just assume that whenever there is an update in, I'm going back, whenever there is an update in any of this cell, you update the matrix profile index to point to the right nearest neighbor. That's what is happening going forward in here. So the overhead is negligible, because whenever you are checking the minimums, you just keep the indexes. All right, so then I would like to explain, so we are not done actually. So the algorithm, I'm going back, the algorithm we are seeing here is not yet the finalized version. We need to explain this particular thing in a greater detail, because we need to understand like what changes we need to make in the matrix profile, or in the matrix in general, for which we are creating the profile. So we need to understand the trivial matches. So imagine that this is the query, right? And you have the time series, and you say that what is the nearest neighbor of this query in this time series? And you say that, okay, I slide it across, and I find that this is the nearest neighbor, which is happened to be at location 50. And if you say that, okay, what is the next one? And the next one actually will be right beside it, maybe in 49 or 51. And that's not interesting, because it's trivial. We know that, okay, they are highly overlapping, and it's not giving me enough exciting information. So if I go back, so you see that. Now the question is then, what is the second best match should be? So basically what we are going to do is we are going to say that if I find a neighbor here, the first neighbor or whatever neighbor, we will exclude this region as the starting position of the match. So we'll say that within this zone, I will not tolerate any nearest neighbor, which essentially forces the algorithm to find the next best somewhere else, which is more interesting. The more special case in our matrix profile scenario, where we are taking the query from the time series itself, and we know that it will match with the time series itself, right? So this query is taken from here, and it matches there with 0 distance. And obviously we know that, and we don't want that. So what we are going to do is we are going to, again, use an exclusion zone to find the true nearest neighbor, which is non-trivial, as we define it, because any match that is with itself, or a overlapped version with itself, is basically a trivial match. So that's something we really want to avoid, and that's why we define this exclusion zone. How do we define it? Basically, we keep the distance profile or matrix, the distance values as not a number, so it does not hamper our minimum or maximum functions. And so what should be the size of the exclusion zone? So here, so let me explain the impact. So in the matrix, what does it mean? It means that in the diagonal, you exclude some values that are within this thing. And in the code, it means that you say that around the diagonal from minus m over 4 to m over 4, you explicitly insert not a number. And if you do that, then basically you are saying that even if there are very small numbers here and here and here, they will not be ending up in this matrix profile because you explicitly made them not a number. And size of the exclusion zone actually depends on many things. I mean, it depends on the smoothness of the time series, how big you should be putting it. Say, it's less sensitive. We used m over 2 for all the cases. So minus m over 4 to plus m over 4 is actually m over 2. And we use that. But you can build more interesting data adaptive techniques to find that exclusion zone, which can still be an interesting exposition. Then the question is, OK, given this algorithm, we take the time series, we row by row calculate the distance profiles and take the minimum, and gives us n square n log n cost. But the fact is that it has a specific order of evaluation, right? So from left to right, from I equals 1 to n minus m plus 1. So this left to right ordering can actually create a bias in your evaluation, because sometimes we may have data starting at the weekend and then ending on Friday, or sometimes it can be starting on Monday and ending to Saturday. So depending on where you start, the interesting patterns location may change. And that's something you don't want, because in that case, basically, if you run it and you see that the algorithm is taking too long and you stop it, a good portion of your data will not be even explored. So that's why instead of doing it in a fixed order, let's randomize the order. And what it gives actually an averaging effect across different data set properties. So if your data has a different, I mean, starting at Monday or Friday, it doesn't matter because it'll averaged out by the randomization of your evaluation order. And that something is very interesting, and it provides also a diminishing return that enables you to stop early with an expected gain, higher expected gain. And not only that, since the rows are independent, you can interrupt and resume your operation anytime later without basically the necessity of recomputing from the scratch. So just adding this highlighted segment, we can actually get useful properties. And let's see some of that. So let's say this is the exact matrix profile of a time series. And we have in the x-axis the iteration. So as we pick a random time series, calculate distance profile, and take the minimum, we calculate the approximate, the root mean squared error between the approximate matrix profile and the final output matrix profile. And naturally, the error goes down and down. Initially, the error is high, and it goes down and down. But the fact that within 1,000 iterations, say in this case, I don't have the number of entries. Oh, 10,000, yes. So for a 10,000 long time series, if you do 10% of the work, then basically you converge to a very good close matrix approximation of the matrix profile. So you can stop early if you do the randomization. Otherwise, it'll not be like this. It'll be more like a slope 1, negative slope 1 curve. And here is a video that can show the algorithm in action. So this is the time series. This is the best so far matrix profile, and this is the best motif. And here is it's working, 0.1% done, 0.2% done. It goes down and down and down. And here the best motif. And once we hit, say, 0.2%, we can stop, and we will show the final answer. So it goes down and down and down. We find the best motif. And we skip the next 99%, 99.08% of the calculation, and this is the final output. If we see them side by side, then this is the final output. This is the output after 0.02%. And obviously, it's a noisy version of this. You can see that. These are the noisy segments. And this is much smooth, very clean. The output, they are from different locations as well. So the best motif here is at this location, while the best motif after 0.2% is done is somewhere else. But their shapes are almost identical. So what the bottom line is that you may wait till 100% done, which can take long, long time, but maybe after 0.2%, you can get what you want. All right, so then the question again, can we improve STAMP? So I'm going back to note the idea that we named the algorithm Scalable Time Series Anytime Matrix Profile STAMP. So A stands for anytime, meaning that it is a randomized order of evaluating the distance profiles and so on. So now we are going to talk about the STOMP, which is Scalable Time Series Ordered Matrix Profiles. Question is, can we improve STAMP with a theoretical algorithmic improvement? And answer is yes. So STAMP computes distance profiles in row by row order and don't use any overlap between the rows. But actually, if you think about it, like imagine the 3 successive columns, rows here. Those will be done for 3 successive windows which share a lot of points together, right? And we are not using that in STAMP. We are basically calculating mass for each of these windows independently and taking the minimum. Can we use that overlap? And the answer is yes, and we can then make an order n square algorithm, not n square log n, and that's the STOMP algorithm. And here is how it is. This is our working formula, if you recall from the very beginning. And I just replaced this part, which is, again, the dot product, which is Ti, Tj, basically the subsequence starting at ith position, subsequence starting at jth position, and you just take the dot product up to the mth position, starting at I and j. And you have this. So question we ask is that, and obviously you know that we can calculate the means and standard deviations using move mean and move standard deviation functions. Then question is, can I use this, reuse this, right? And answer is very, very simple. Yes, if we have the Ti, Tj, or dot product between I and jth subsequences, we can use it to calculate the dot product between I plus 1 and j plus 1 subsequences, right? Because that means that it is simply subtraction of the left entry and the addition of the right entry. You just do that. It's a single constant operation. And we can use that actually to create STOMP. So STOMP is this, that you pre-compute all the means and standard deviation in purple. You pre-compute all the first row and first column, which is supposed to be identical. And then you iterate over rows while you calculate this row, given that you have a local variable that stores the previous row. And you just take the values with a constant operation from the previous diagonal entry. And if you keep doing that and then maintaining the matrix profile and an index, then basically you appear with the STOMP algorithm. And this is a quadratic time algorithm, not n square log n, because you are reusing the dependency between the 2 rows. And then again, you can ask the question that, hey, you removed the dependency, you said that independent rows are good. Now you are adding the ordering, so you destroyed that even. So question is, can we restore randomization? Because if you recall, I'm going back, here we are again doing row by row calculation, and so in that case, if we have a Monday starting or a Friday starting, will be depending on the starting point. And that can be done by diagonal processing. So basically, instead of row by row processing, we'll say that we'll randomize the processing of the diagonals, because diagonals depend on each other. So as you see, that this value depends on the value diagonally in the previous column or row. And similarly, this value depends on the previous row column value. So you can randomize these diagonals and calculate the distance profile in that way, and again have the anytime property, which we call scalable column independent matrix profile. And finally, you can say that, okay, how can you parallelize this, right? So going back to STOMP, not the SCRIMP version or column independent version, if you think about it, so this value depends on this one. This value depends on this one. But when you are calculating this, you don't need anything that this guy needs. Right? So all of these diagonals, since they are independent, you can run this little picture means that you are thinking of a thread in a GPU or in a parallel environment. So basically, you can say that one thread will be responsible to calculate just this value and update this P2. Another thread will be responsible to calculate this value and update P3 and so on. And for each row, you will create a set of threads. They calculate the matrix profile, come back to you, and then for the next row, you create again another set of threads. They calculate the distance and so on. So if you parallelize this way, then basically for this whole thing, one update of this thing will be calculated in one parallel run of all of the threads. And if you think, say, n is 100 million, which can easily be that many threads, you can easily schedule in a modern GPU. In a modern GPU, you can have, say, 2 to the power 70 threads, parallel threads, which is more than enough that we need. So this is the best thing, that you can actually, the whole computation, what we did essentially is that we divide the calculation in so tiny pieces that we can now understand how to parallelize this and extract the maximum speed we can have to scale to very, very large time series. So the timings are here. So STAMP takes 24 hours for 2 to the power 20. STOMP takes 5 hours. If you port it to GPU, then it gets to 2.5 minutes. And this is for 2 to the power 20. For M equals 256. 2 to the power 20 is 1 million, close to 1 million. You can imagine that way. For large data, if you think about, like, say, can we go even bigger? So we tried these two examples. So 400 is the small m, and 100 million is the largest n. And obviously, STAMP, STOMP both cannot do that. We didn't do it. It is estimated. But using the GPUs, we could do it 12.3 days. And we really did it. We waited for 12 days to really finish that thing, just to be able to say that, yes, we did it. No, I'm just kidding. So, but the good thing is, at least, say, for example, a reasonable size, 17 million, you can do it in 9 hours, which is reasonable in a way that at least within a day, you can expect the results to be out. How does STOMP, STAMPs, GPU STOMP, how do they compare with the other techniques? By other, actually, I mean that if you think, like, fundamentally how these algorithms are different from existing techniques. The fundamental difference is that we do not do pruning-based work, right? So most existing technique, people will say that, how about indexing? Or how about lower bounding-based pruning? And those kind of work is the most common trend that people do to calculate distance, similarity metric, similarity measures, distance profiles, and so on. Quick Motif and MK are the two algorithms that actually fall in those categories. And if you see the comparison, that STOMP is independent of M. So as you vary M for the same n, which is 2 to the power 18, the space requirement is identical, timing is almost identical. While these algorithms are non-monotonic. Not only they just vary, they are non-monotonic. So for example, here, you doubled the M, you need less space. I don't know why. Actually, I know because of the pruning thing. So you can prune more, and you need less space. But the thing is that the whole space requirement is dependent on the data properties and many other stuff that you don't want your algorithms to be. Because we are creating this as a black box, and that's the way it will be useful for all domains and all different application areas. So MK is out of question, so that's no comparison. The only thing that we should also mention is that here, for example, you may say that it uses more space, but it gives you fast results. But what results, right? So if you think about that, so STOMP produces the full matrix profile. So you can ask that, OK, what is the first motif, then second motif, then third motif, and so on. But quick motif is only for, say, a given number of motifs. After that, if you say that create quick motif for k, and then you say that what is the k plus 1th motif, it cannot say that because it does the whole thing assuming that it knows well before that what is the output required. And based on that, it prunes. But here, you don't need to know that thing. You can explore using the matrix profile after STOMP produces the matrix profile as an output. And I think I will skip at this point the progress bar question, because I'm almost there. And this brings me to the open problems. And that's something I'd like to spend a little more time, which is if you think about the lower bounds, the algorithms, mass is n log n, and matrix profile is n squared. can we build inexpensive lower bounds to even make them faster? So can we make an order n lower bound or for distance profile, or order n log n lower bound for matrix profile? If we can, then basically by adopting those pruning techniques, we can make these matrix profile algorithms even faster. We can say that why Euclidean distance and those lockstep measures don't cover. So say, for example, another lockstep measure is L1 distance. I tried to, actually, I will submit, I tried to port mass for L1 distance and I couldn't, because so you cannot calculate L1 distance or sliding L1 distance using convolution. That's what I felt, but I would really love to see if someone does that and make a mass version for L1 distance. We can adapt to non-elastic, non-lockstep measures, elastic measures, and those will be definitely valuable because the scalability is the issue. I cannot imagine making a distance matrix profile for warping distance, time warping distance for 100 million time series. That's like really challenging. We can say variable length matrix profile. So we have a parameter m, which is a given parameter, and we discussed this after Eamonn's talk that, okay, what should be it? And it has a domain specific meaning, right? In ECG, it may be 5 seconds. In taxi data, it may be a day. But question is, how about for a same domain, you don't know it, say you say from 1 day to 5 day, or from ECG, 5 seconds to 10 seconds. Then how do you calculate with some degree of fidelity the goodness of them? So should I take the neighbor of 5 seconds long window, or should I take the neighbor of 2 seconds long window? Which one should I keep in the matrix profile? I don't know. So that's something we should explore. Scalability, like we have this GPU version, we see where the computations are independent, but we haven't scaled it in a horizontal way. We cannot really say that I just throw in money and I will solve whatever size problem it is. I cannot really do that. We need to be able to go in that state, right? That whatever is the size, like a 10 billion long time series, you just give me money, I'll do it in 1 day. We need to go to that scalability approach. And then we can obviously bring in domains. So we can say that, okay, can we have data adaptive ordering, right? So we have seen that we randomize the ordering to get the anytime property. But can we do a different ordering, which is dependent on the data? Because I know that the important data is in the weekend, or I know that the important data is after the surgery. If we know those things, can we use those to order the anytime algorithm even better? And also we can use the annotation vector, which we can even learn. Instead of just guessing or getting it from the domain experts, can we learn it from the matrix profile? Can we see where the non-interesting parts of the matrix profile exist, and can we systematically decrease the weight of that? And finally, actually, visualization is very important, which we used MATLAB here. For many people, I mean, if I give this talk in, say, graphics people to graphics people, they'll say that, oh, what are you showing us, right? So these are very low-level visualization, just good enough for a data miner like us. But if you have visualization skills, you can make great stuff from matrix profile, because it carries a lot of information, which we are exploring, like how we can exploit those information in those matrix profiles. So a good visualization can take you a long way. So these are the open problems that we could think of. And I am honest, some of those I tried, I failed. Some of these I haven't tried, but I'll be happy if some work from me, from the audience, or in the next KDD comes up. So with this, I will end. I'm that poor guy. Shoot me.